Okay, thank you everyone for joining this session of the demonstration video. So the today's topic is how to include the technology libraries in LTSpice in order to find the characteristics at the lower technology nodes as and when required. So at the very beginning of this talk, I must uh, acknowledge the help from Dr. Sanjay Vidyadharan. He is an assistant professor in the web division of uh, Pilani, uh, as because his website is going to be alluded to during the talk. Thank you, Sanjay sir. Okay, over to you, Jaideep.
Good afternoon, everyone. Today I'll be covering the two technology nodes which are 180 nanometers and 45 nanometers, and we'll be observing the changes in the circuits when we do parametric sweeps or changing the width, and we'll also be observing certain key features like propagation delays, rise and fall times, and so on. First off, I'll be referring to Vidyadharan sir's website to get the technology library for the 180 nanometers. So you can just click on this link and we'll find all of the files over here. So the first step is to actually download the TSMC 180 nanometer file and store it in this particular directory. I'll show that as well. So after downloads, you can copy and paste it in this particular directory as shown in this slide. And after opening the TSMC 180 nanometers, we'll see three files. So the TSMC 018.lib goes into the subdirectory over here, whereas we can download the CMOS N files and CMOS P files and store them in this particular directory. And if someone wants to explore, they can always check out Surya sir's official BITS website where he's mentioned several other technology nodes. I'll start the LTSpice demonstration now. So the first step is actually getting the. I'll be demonstrating a CMOS circuit first of all. So we can take the CMOS N which we have downloaded previously. Now taking the CMOS P as well. First off, I'll just be simulating a simple DC analysis to show the VTC curve. Here I'm also connecting the body. So for the PMOS source voltage, I'll be giving 1.8 volts. And since we're doing the DC analysis, I'll actually do a sweep of the voltage from 0 to 1.8 over here. For that, we can include the SPICE directive. And first off, I forgot to mention one thing. We include the uh, initial library that we downloaded. We'll be doing a DC sweep of the V2 source. You can start from 0 to 1.8 volts. I'll be giving output terminal as well. Here I'm considering a capacitor of 50 femtofarads. And when we observe the drain voltage of the NMOS or the drain voltage of the PMOS, we can observe this particular VTC curve. Now, for instance, if you'd like to do a parametric sweep of the widths of the NMOS and PMOS, we can see the VTC curve shifting. For that, we'll need another SPICE directive. Initially, let me declare the variable W as the widths of the NMOS and PMOS. Since we are working in the 180 nanometer technology nodes, I'll declare this as 180N. I'll be sweeping the width from 400 nanometers up to 800 nanometers in steps of 100 nanometers. After getting the DC simulation, we can observe the range of the VTC curves. As we increase the width of the device, it becomes a better PMOS and worse NMOS, and we see the VTC curve shifting towards right. Now to observe parameters like propagation delays or the rise and fall times, we have to observe the transient analysis. For that, I'll change this back to 400 nanometers. And as you know, the width of the PMOS should be twice to account for the mobility. And here I'll be giving a pulse. So we can take this as 0, 1.8. I'll assume a delay of 2.5 nanoseconds and a rise time of 10 pico. Now changing the simulation command to transient analysis, we can observe the simulation to go on for around 20 nanoseconds, running the simulation. Here this is the output voltage. Here is the input voltage. In order to observe the propagation delay, we can observe the time difference between zero point 0.5 of the amplitude of the input and difference between zero point 0.5 of input amplitude and the output voltage amplitude. So you can make the use of cursors. Since we've given 1.8, I'll try to keep this around 0.9. Similarly, using a cursor for the input. The horizontal cursor values can be noted and the difference can be calculated between the output and the input amplitude at zero point 0.5 of 1.8. If we just want to calculate the rise time, we can zoom in on the rising edge. Now rise time, we can take the difference in the time for the output to reach on point 0.1 of its maximum to 0.9. So around 0.18. We can make better adjustments by zooming in further. We take zero point 0.9 of 1.8, it should be around 1.62 volts. And then the horizontal time difference will give us the rise time. And similarly for fall time, we can take the time difference between the output going from zero point 0.9 of its final value to zero point 0.1 of its 1.8 value. Whereas if one wants to find the noise margin, we can go back to the DC analysis and get the appropriate values for VOH, VIH, and VIL. So there are two ways to go about this method. Either we can find the 2 points where the slope is -1 and consider those points themselves to be VOH and VIL and VIH and VOH respectively, which would be these points. Else, we can take the values of VIL as this value, VIH as this value, and we can look at the graph where it saturates and take that value as the VOH. So just before it touches 1.8, and VIH can be taken around this place just before it saturates to 0. This is how we can go about getting the noise margins. And now switching over to the 45 nanometer technology node. Here I'll be including the text file which contains the 45 nanometer technology node as a SPICE directive. The main purpose of this exercise is to see the difference in the parameters of the CMOS circuits when switching between technology nodes. I'll include it over here. Similarly, we can build the CMOS circuit, but this time
Excuse me, Jaideep, can't you
yes,
just
sir.
copy your circuit from the draft 3 file?
So I'll copy the circuit from one of my previous works, sir.
Yeah, yeah, please do. Oh,
Similarly, we can start with the DC analysis of the 45 nanometer technology node CMOS. But over here I'll be sweeping the value from 0 to 1 volts. Here we can observe the switching threshold to be around zero point 0.5 volts. And similarly, we can calculate the noise margins by considering the slopes as -1 over here and -1 over here. The key outcome of this exercise is that we see an improvement in the robustness of the circuits as we go from higher technology nodes to lower technology nodes. If we actually measure the values, we can see a significant decrease in the noise margin. We can see a significant improvements in the parameters. Similarly, you can also perform the parametric sweep by changing the variable again. Here I'll be sweeping the width of the PMOS and NMOS from 400 to 600 in steps of 50 nanometers. And we can observe the output voltage again. We can also perform the transient analysis to observe the parameters like propagation delay, rise time, and fall time again. Here I'll be changing the input voltage source to a pulse. I'll change the simulation command again. You can observe the transient analysis for about 20 nanoseconds. If we assume this time interval, we can calculate the propagation delay as the difference in the time between the 50% of input voltage and 50% of the output voltage, around zero point 0.5. Here we can get the time difference between the two. We can delete the trace of the input voltage and find out the rise time and fall time by considering the horizontal time difference between the zero point 0.9 of the 1 volt and zero point 0.1 of the 1 volt again. This will give us the fall time, and here we can take from point 1 to point 9, and then that will give us the rise time.
Okay. Okay. Is that all, Jaideep?
Yes, sir.
Okay. Any questions from the audience? Like if you have any doubts or something, you can of course um, ask now, or Jaideep will be available with us for the future as well. Okay. So I'm going to stop this recording now because this will essentially be one video, one demo video for the LT spicing. After a short while, Jaideep will be like demonstrating how to use Verilog AMS as well. Okay. Please stay tuned.
Thank you, sir.